If you've spent a lot of time with circular functions, then you might have noticed that there are a lot of symmetries when it comes to the unit circle. In this video, we explore the key symmetries of the unit circle. For those who don't know me, my name is Chris Iannazzoni. I've been tutoring for about 2 years now, and I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. The most obvious one that we come across is this idea of periodicity. Sine, cos, and tan are all periodic functions, where sine and cos are periodic about 2 pi, and tan is periodic about pi. This quirk can be used for calculating circular functions that have a fixed angle in addition to their variable angle. For example, we're told that sine theta is equal to 0.43, and we're told to figure out what sine of 2 pi plus theta must therefore be. Using periodicity, we can say that 2 pi plus theta is the same thing as just theta. Hence, we can say that sine of 2 pi plus theta must therefore also be 0.43. This property works for any positive or negative even number of pi when it comes to sine or cos. For tan, it doesn't have to be even anymore. It could be any integer value of pi. Now that we've looked at the full period formulas, let's look at what happens when we only go halfway. Alright, so first up, pi plus theta. What does that mean? Well, if we imagine that theta is some first angle quadrant, then we could label the coordinate at that spot using our values for sine and cos. Pi plus theta means that we are starting at pi and then adding an additional theta. This is going to take us from the first quadrant all the way to the third quadrant, where the signs of the x and y values will swap, but will otherwise be the same value. This result tells us that both sine and cos will flip their signs if you have pi plus theta in the brackets. When it comes to tan, however, nothing happens. This is because tan is sine divided by cos, and when you have a negative divided by a negative, those negatives cancel out and you get right back to just being positive. We actually saw this result earlier when it came to periodicity. Pi minus theta is similar, except when we start at pi, we're now going to go backwards by theta since it's minus theta. This is going to take us from quadrant 1 all the way to quadrant 2. Where only the x is going to flip its sign. This means that sine of x will stay the same, but cos of x will flip. As a consequence, tan will also become negative. This is because anytime there's a mismatch between sine and cos, tan will go negative. Once again, let's explore this with our first quadrant reference angle. Just a quick note here. You can pretty much solve any of the things we go through here using this approach. That way you don't have to memorize each individual result. You can just flip things around and then see what happens. Anyway, negative theta simply means that you're going in the clockwise direction rather than the anti-clockwise direction. Another way of thinking about this is just reflecting your point in the x. When we do that, we're going from quadrant 1 down to quadrant 4, where the y values will change, but the x values will stay the same. This means that sine will change, cos will remain the same, and tan will also change, because again, there's that mismatch. Almost there. The quarter period formulas can be found using the exact same approach. Let's give it a shot. Okay, so this one just means that we're starting at pi on 2 and then going backwards by theta. This one's a little bit different though, because it ends up being the case that we stay in the same quadrant. What happens here is that the x and y are swapping their positions. Cos becomes sine, sine becomes cos, and tan actually flips on its head, since the numerator and denominator have flipped positions. This is similar, but we're going to end up in quadrant 2 because we're adding theta. Now, under these circumstances, 2 things actually happen. We get the effect of swapping the x and y, but we also get the effect of being in quadrant 2, meaning that our x is now going to become negative. So, we can observe that cos has become negative sine, and sine has become cos. And finally, when it comes to tan, we're also going to get a double effect, where it's going to flip on its head because the x and y have swapped, but it's also going to become negative because now there's a sign mismatch between sine and cos. The last thing we'll look at is the Pythagorean identity. You've likely seen it before. It's just an equation that relates all the lengths of a triangle to each other. In the context of circular functions, you can rewrite this identity in terms of just sine and cos, because sine and cos give you the opposite and adjacent lengths respectively. Just remember that the hypotenuse is 1 because the unit circle has a radius of 1. Why does this matter? Well, consider the case where you only know one circular function out of the 3 of them. You can use the Pythagorean identity to find the other 2. In this example, we know that sine is 3/5. So all we're going to do from here is plug that into the Pythag identity and then just rearrange for cos. This is going to require us to square root both sides, giving us a plus minus answer for the cosine. This is where the domain becomes important. The fact that our domain is between pi over 2 and pi means that we're basically talking about the second quadrant, which means that cos must be negative. Once we know what cos is, we can always find tan by just doing sine divided by cos and then just simplifying that result. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.